Well, suppose you work for a company and your boss comes to you with a problem.
Houston, we have a problem.
Yeah, kind of like that. So suppose your company needs a closed rectangular box that will hold 16 cubic feet of material. The top and bottom are made from material costing 10 cents per square foot, and the sides from material costing 5 cents per square foot, and you want to make the cheapest box that still holds 16 cubic feet. Save your company some money. So find the dimensions of the box that can be made with minimal cost. And you know, if your company is making like 100,000 of these boxes, you can imagine how much money you'll save them, and perhaps then you'll be worth your income. All right, so if x is the width, y is the length, and z, now keep in mind, since x times y times z equals 16 cubic feet for our box, then z would be 16 divided by x times y. So our top and bottom are each of area xy. The two sides are each of area y times 16 over xy, which is 16 over x, and the two other sides are x times 16 over xy, so 16 over y, and the cost function that we're going to minimize is, there's two of these at 10 cents a piece per square foot times x times y square feet. There's two of these times 5 cents per square foot, so 0.10 times 16 over x, same story with 0.10 times 16 over y. So that is the function, the cost function that we wish to minimize. Well, partial with respect to x of this function would be 0.20y minus 1.6 over x squared. The partial with respect to y would be 0.20x minus 1.6 over y squared. So setting cx equal to 0, partial with respect to x equal to 0, that's this one equal to 0. If we multiplied both sides by 5, we'd have y minus 8 over x squared equals 0, or y equals 8 over x squared. We substitute that into our cy equation. You know, we're trying to make both of these partials equal to 0, and there's no obvious look at it and write down an answer, so we're going to have to solve this equation when we plug this in to cy. So here it goes in there for y. This y squared is going to be replaced with 8 over x squared. So we got 0.20x minus 0.16 over 8 over x squared, and if you simplified that, it's 1/5 x. I guess you knew what that was. And this 0.16 over 8 is 0.2, and then there's another over 8, so 0.2 over 8 turns out to be like 1/5 over 8, which is 1/40th. And this x squared, which x to the fourth would go to the numerator. And now we have an equation that's a fourth degree equation. And it's pretty easy to solve that. Certainly 0 is a solution. But that one, well, that one would make for an interesting box, because these two sides will then be 16 over 0. So that's kind of out. So we'll go to a solution that has a reasonable answer, and that would be another one. If you factor it out, actually multiply both by 40 and factor out an x, I think you get something like x cubed minus 8 equals 0, and so therefore x could be equal to 2. And of course, since we factored out an x equals 0 is another solution. But 0 is out, right? We forget that one. You also get two complex number solutions, but they don't have any effect. How about this? Has a box of volume 0, so no box. At all would be a better answer for that. Okay, so that solution is not interesting, but 2 is. So if x is 2, then y, which is 8 over x squared, is also 2. And at the point where x is 2 and y is 2, keep in mind, don't forget x times y times z equals 16. So that would force z to be equal to 4. And so is it a maximum or is it a minimum? Well, the second partial of x for this one would be just 1.6 over x cubed. If you take the derivative of this part, you get 0 the derivative of this. It's a little tricky, but think of it as negative 0.8 times x to the negative 2. So you get negative 1.6 times x to the negative 3, or actually, since the two negatives cancel, you get 1.6 over x cubed. Similarly, the second partial with respect to y, 1.6 over x cubed, and the mixed partial of this with respect to y is 0.10, of this with respect to x, 0.10, just as we suspected. We have a theorem on that, after all. So put in the 2, so it's 1.6 over 8. This is 1.6 over 8, so the partial with respect to, second partial with respect to x, 1/5. Second partial with respect to y at the point 224 is also 1/5, and the mixed partial is 0.10. And so cxx times cyy, 1/25 minus 1/100th, which is a positive. And since this is positive and our d is positive, we know it to be a minimum point, and the graph, I hope, will show this to be true. I'm trying my best to show that this is true, that when x is 2 and y is 2, we get a minimum cost of, I don't know what the cost is, but looks like it might be something like maybe, let me see, x is 2 and y is 2, the cost would be about here. I'm keeping my eyeball in as I rotate it. Maybe $2.50 a box. I haven't tried that, but let's see if we evaluate this when x is 2 and y is 2. We get 20 times 4, which is that's 80 cents, plus 10 times 8, that's another 80, plus another 80, so $2.40. And I think you can see that about $2.40 would be the c value. Remember, this is a function of the two variables x and y, so our c value would be about $2.40 there. Okay.